In this video, I'm going to work through three examples of integration by substitution. The first example is the integral of log x over x dx. Here we're going to let u equal log x, and then du will be 1 over x dx, because 1 over x is the derivative of u, and we also have 1 over x in the integrand, and so this will work out to simplify our integral quite considerably. So when we make the change, we'll get the integral of u, which is log u, du, because the 1 over x dx is just du. So when we take find the antiderivative, we get 1/2 u squared plus a constant. And now we back substitute and we get 1/2 of the quantity log x all squared plus a constant. So that's an example of a simple integration by substitution, and the way I've done it is to pick a part of the function to be integrated which has its derivative also in the function to be integrated, so that I can simplify by substituting du and u into the integrand. Let's look at the second example. And the same kind of thing is going to happen here. We have e to the root x divided by root x, and we want to know an antiderivative for that. Well, if we had e to the u here, we would know how to integrate the exponential function. So let's let u equal root x and see what happens. When we take the derivative of u, we get 1 over 2 root x, because the derivative of root x is 1 over 2 root x. So we get du is 1 over 2 root x dx. Now we have to do a little bit of simplification here. We cross multiply the 2, so we get 2 du is 1 over root x dx. We do that because it's 1 over root x dx that we have in the function we're integrating. So now we use this information to rewrite the integral as the integral of e to the root x divided by root x dx is 2 e to the u du, and we know how to integrate e to the u du. It's just e to the u. We multiply by 2 and add a constant of integration. The final step is to go back to the original variable x, so that you actually have an antiderivative written in terms of the variable that the problem gave you to begin with. This is again a simple integral where we've identified a simplification by substituting a function or changing the variable in a way that where we can actually have the derivative of the new variable sitting in the integrand. And the final example in this set is the definite integral between 0 and 1 of x cubed plus 5 to the power 6 x squared dx. Here we should let u equal x cubed plus 5, because then du will be 3x squared, and we have an x squared here in the integrand, the thing that we're integrating, the function we're integrating. So we flip the 3 over to the other side, and we get x squared dx is 1/3 du. So when we shift the variable from x to u, we're going to change x squared dx to 1/3 du, and that tells us the way that these two variables are related. Now, when we go to do this integral, we are doing a definite integral, not an indefinite integral. And so this will change the way the rest of the solution goes. You have a choice at this point. You can decide to write in your answer, I will now evaluate the indefinite integral, and then at the end I will evaluate the definite integral using the antiderivative I find. Or you can keep it as a definite integral throughout, and that's what I've done in this example. When we make the substitution, we're going from x equals 0 to x equals 1. We're changing to u going from 5 to 6. Now, where did those come from? Well, if you put x equals 0 in the formula u equals x cubed plus 5, you get u equals 5. And if you put x equals 1 in this formula, 1 cubed is 1. So u, the value of u when x is 1 is 6. So this integral is between x equals 0 and x equals 1, but in terms of the new variables, it goes between 5 and 6. And so when we substitute, we get u to the 6th, and then x squared dx is 1/3 du. Now the 1/3 factors out in front because it's a constant, and we're just integrating u to the 6th du. That's a power, and so we know how to integrate that. We have 1/3 still, but we'll get 1/7 u to the 7th. We add 1 to the exponent and divide by the new exponent. So we get 1/3 times 1/7 u to the 7th. And what I've done here is to write on the right-hand side u equals 5 to u equals 6. And this is a common notation that's used to record the limits of integration when you're doing a complicated integral. And we have the antiderivative inside the box here, and we're going between 5 and 6 to evaluate that to get the definite integral. So now the final step is 1 over 21, so that's 3 times 7. We substitute u equals 6, so we get 6 to the 7th power, minus 1 over 21, 5 to the 7th power. And this number is the value of the definite integral that we were going to calculate. As I say, there's a couple of ways you could have done this. We could just have integrated and found a general antiderivative and then as a separate step evaluated it. We could have substituted the value of u back towards the value of x and then use the value of x going from 0 to 1. So there are a number of ways that you can handle a definite integral. The one I've done here is the most systematic and is usually the simplest way and most assured of making sure that you don't forget any of the parts of your problem.